So the EM algorithm is slightly complex. Let's try to see another example that involves the zero-inflated Poisson model, which I call the ZIP model. So here's a motivating example for why the ZIP model can be useful. Let's suppose that you are interested in drinking habits of teenagers, and you go to school and administer a survey to a bunch of teenagers, a total of N teenagers, and for each of them, you ask them how many alcoholic drinks you have on a given day. Let's say that after collecting the data from N teenagers, this is the histogram of the number of drinks that we observe. Right? Or you can see that a bunch of teenagers report that they don't drink, and then there are some that drink like 1 per day all the way up to 6 per day, which these teenagers might be in trouble. Right? But we're interested in teenagers in trouble. All right, so how do you describe this distribution of teenager drinking habits? It's counts, right? How many drinks someone has on a given day. Can you use the Poisson distribution? If you try to model it using a Poisson distribution, and you will see that the model is not going to work very well because a Poisson distribution does not quite explain the large number of zero values that you observe. Instead, what is more reasonable is the zero-inflated Poisson model. It actually is still a mixture model for counts, but in this case, it's going to be a mixture of two populations of teenagers. Let's suppose that there's one population A, which is going to be having membership probability pi. And for everyone from population A, these are essentially individuals who never drink. You also have a population B, which are the remaining teenagers. It has probability 1 minus pi. And for the teenagers in this class, the number of drinks that they have on a given day follows a Poisson distribution with mean lambda. And your observed data is actually the mixture of these two groups of teenagers. Here's the data generating process I had for the earlier histogram, where I had the pi true parameter equal to 0.7 and the lambda for the population B equals to 3. So for the 30% of teenagers who come from the second class, on average, they have 3 drinks per day. You can see this is like how we generated data from the mixture distribution. We first generate the latent group membership. It's going to be either 0 or 1 in this case. And the counts of number of drinks is either going to be exactly 0 if someone comes from the first class, or it's going to follow a Poisson distribution given by R plus, where the rate parameter is equal to 3. All right. So the ZIP model is actually very useful in practice. You can probably think of a ton of possible events of counts where it has this structure. If you're interested in people's smoking habits, maybe you end up with the majority of people who never smoke. So in these cases, the ZIP model is going to be very useful. Of course, there are a lot of extensions to it as well. For our simple ZIP model, there are 2 unknown parameters, which are pi and lambda. Pi is the proportion of individuals from population A, so it's essentially people who never drink. And lambda is going to be the mean or the expected number of counts of alcoholic drinks for those who come from population B. So if we can see each individual's membership, so is this teenager a never drinker or someone who drinks? If you observe the group membership, A or B, for each teenager, then that's the case where you have the complete data. Right? In that case, if you want the MLE of pi and lambda, it's actually very straightforward. Right? That's exactly what you learned in your earlier classes, where if you want the MLE for a proportion, simply just count what proportion of individuals are from population A. Right? If you want a lambda estimate, you take the reported number of drink counts for those individuals from class B, take the average, that gives you the lambda hat, the rate parameter estimate. Right? However, the thing is you actually don't know the group membership of each teenager, whether they come from class A or class B. Right? So we have to do something similar to the EM algorithm again. Let's suppose that in the data set, the largest number of observations for number of drinks is 6 drinks. this can change depending on your observed data. Right? Sometimes you might end up with some really alcoholic teenager who drinks more than 10 a day. So let's suppose that the largest is 6. Then in this case, your observed data can be denoted by NKs, where the K ranges from 0 all the way up to 6. Right? Essentially, NK is the number of adolescents who reported that they have K drinks per day. That's our observed data. Right? Our observed data is going to be a vector of the counts. How many teenagers out of the total N reported they have 0 drinks, how many report they have 1 drink, and how many reported they have the maximum number, which is 6 drinks for this particular data set. What we don't observe is out of those who have 0 drinks, how many of them are from class A, who are the never drinkers, right? Let's call this NA, which is the number of people in class A, which should be a subset of this N0, the individuals who report they have 0 drinks. That's in reality missing, right? That's our missing data. And then in this case, we can denote our missing data by MMIS, which is going to be NA and MB. MB is essentially out of these individuals who report they have 0 drinks, how many of them are not the never drinkers? They just happen to be having 0 drinks on this day, right? So if we know N0, that's observed, and we know how many individuals out of N0 are from class A, the never drinkers, we naturally know that the MB is going to be the difference between these two. Okay. So NK is the number of observations that report having K drinks. Right? The number of observations that's equal to reporting they have K drinks equals to K. We can use the multinomial coefficient to see how many different ways they can be distributed over the large N observations, right? If you write the corresponding multinomial probability mass, it will be given by this form. So the probability that we observe the observed data given pi and lambda is given by this model over here, where we have large N factorial divided by N0 factorial and 1 factorial all the way up to N6 factorial. This should look familiar to you from the investment model example in Bayesian, right? And then times the product over all possible classes, counts of drinks ranging from K equals 0 to 6 of what is the probability that Y is equal to K. So the randomly sampled teenager reports having K drinks raised to the power of NK, because we know there are NK teenagers who report that they have this specific number of drinks. So how does it depend on pi and lambda? Essentially, here for each possible K that's greater than 0, so 1, 2, 3, 4, 5, 6, we know that for a randomly sampled teenager, the chance that they report having K greater than 1 drinks, exactly K drinks, will be given by first the chance that they come from class B, so the teenagers who indeed drink somewhat, times given that they come from class B, what is the probability mass that correspond to they have exactly K drinks? So that's the Poisson density, Poisson mass, right? Where K here is 1, 2, 3, 4, 5, 6, so the value is greater than 0. The probability that a randomly sampled Y, so a teenager's reported number of drinks, is equal to exactly 0, so the K equals to 0 case, will be given by 2 possibilities, right? It's either this teenager comes from class A, who we know for sure they don't drink, so pi is the probability they come from class A, or they come from class B, but they reported they didn't drink on this day. So that would be equal to 1 minus pi, which is the probability they come from class B, times, given they come from class B, the chance that they actually have 0 drinks, right? So this part, e to the negative lambda, is essentially the simplified Poisson mass, where K is equal to 0. Some terms disappear. Okay, so now you know that pi equals K should be equal to these two things, depending on whether K is greater than 0 or equal to 0. If you write down the observed data likelihood, then essentially you need to expand this term, right? And that doesn't look pretty. essentially you have the earlier thing, so the factorial part is still the same, times the part that corresponds to k equals to 0. So py equals to 0, which is the weighted sum of the pi plus 1 minus pi times e to the lambda raised to the power of n0 times the remaining products for k greater than 0, right? K from 1 to 6 of the 1 minus pi times the Poisson masses raised to the respective count powers. Okay, if you were to get the log likelihood from this, you can see that again, part of it involves the log of sums, right? Which is something that we will have trouble breaking down. What might be easier for us to work with is the complete data likelihood, which is the case where you know NA and AB, NB, which the two of them sum up to be equal to N0, right? In this case, if you write down the complete data likelihood, you know that is essentially the joint probability that we observe these counts for each of the classes, but we can further break the N0 class down into NA and NB. We know exactly that NA individuals come from class 0, NB individuals come from this class B, but report 0 drinks. And then there's going to be also the M1 to N case, which are less complicated. Just the 1 minus pi times the corresponding Poisson densities. And this thing is actually proportional to only this later part that does not involve the factorials, right? Why can we do that? It's because whenever we try to find parameters, pi's and lambdas, that optimize the likelihood or the log likelihood, we don't have to worry about the constants that do not involve these parameters, right? So the factorial part can actually be dropped when we do the optimization. If we take the last part of the likelihood and take its log, then we know that essentially the complete data log likelihood, where log likelihood of pi of lambda given n, where n is both the observed and the missing data, NA and NB, is going to be the log of this thing, which is essentially NA times log of pi plus NB times the log of 1 minus pi minus lambda. The minus lambda comes from the e to the power of the negative lambda. Plus, the product becomes summation. The summation over the k classes from 1 to 6 of the nk, which is the power here, times k times log of lambda, minus lambda, again comes from e to the negative lambda, plus log of this constant multiplier in front of it, right? Log of 1 minus pi, plus some constant. The constant is something that does not involve pi and lambda, so we actually can drop it when we do optimization. Okay, so let's try to run the EM algorithm to estimate the parameters pi and lambda given the zip data. Right. Let's recall that in the E step, we've run to get the Q function. Essentially, every time when you try to get the Q function, what you need to do is to figure out what is the conditional distribution of the missing data given the last iteration's parameter estimates, as well as the observed data. So our observed data are the counts for each of the classes, and our last iteration's parameter estimates are essentially pi owed and lambda owed. And we essentially need to figure out, conditioning on these two things, what is the current conditional probability or the chance that we have, say, NA observations from what is the expected number of observations that come from class A and the expected number of observations that come from class C of the 0 class, right? So by definition, we know that the Q function will be given by the expectation of the complete data likelihood, given that conditional distribution I just described of the missing data given the observed and the current pi lambda. In this case, it's going to be given by the expectation of NA given the observed data, pi lambda owed values, times log pi, right? So you can see that it's essentially what was on the last page, this thing over here. But instead, because we're working with the conditional distribution of NA and NB, the missing values that we don't observe, we need to figure out what are their conditional expectations given the observed data and the pi and lambda O's. Right? So here we replace the NA in the complete data log likelihood by the expectation of NA given the observed counts pi odd and lambda odd times log pi. So log pi is this thing. The other thing we need to replace is here we have NB, but instead we need to replace it by the expectation of NB, which we know is the same as N0 minus the expectation of NA, given these things. And everything else is the same as what we had on the last page. It's just these two expectations of NAs that we will need to figure out. So what is the conditional expectation of NA given the observed data in pi odd lambda odd? For each individual I, they can come from two possible groups. They can either come from group A or group B. We don't know, but we can observe their counts. We know that for someone who has a count of number of drinks that's greater than 1, then they definitely come from class B. For someone who has a reported number of drinks equal to 0, there's some chance that they're from group A and some chance that they are from group B. So for each I, the probability that GI, the group membership of the individual, is equal to A, given that YI is equal to 0, is going to be given by the joint divided by the marginal again, right? So the joint is the joint probability that group membership is A and the reported drinks is also 0. The marginal is essentially, regardless of group membership, is either A or B, what is the chance that we observe 0 drinks, right? We know that the joint, the numerator will be given by pi, right? So the probability of the event that someone is from class A and they also have 0 drinks is equal to pi, which is essentially the chance that they come from class A. The denominator is going to be this pi, which is one possibility, plus another possibility, which is this GI equal to B, but YI is 0, right? That's the case where this person comes from population B, but they just turn out to report they had 0 drinks on that day. So the part we sum up together is going to be 1 minus pi, which is the chance someone stems from group B, times e to the power of negative lambda, which is the Poisson density with rate lambda evaluated at k equals to 0. Right. So that's the chance that for each individual I, if they have 0 drinks, then what is the chance that they come from group A? We know that if someone has more than 1 drink, 1 or more drinks, then they have 0 chance of coming from group A, right? So given that, we know that across the n individuals, actually the n0 individuals who report having 0 drinks, each of them has a chance of this thing, of coming from group A, right? So in total, we know that the NA is going to follow a binomial distribution where your count is N0 and the probability of a head is given by this ratio here. But you know, in the E step, we need to plug in the pi odd and the lambda odd over here, right? And we know that for this particular random variable, the expectation is essentially N times P in binomial, right? So you take N0 and multiply it by this probability, right? N0 is the number of individuals who report having 0 drinks, and you multiply it by pi odd, which is the pi from the last iteration, divided by pi odd plus or minus pi odd times e to the negative lambda odd, where lambda odd is also from the last iteration. So that's what you get from the E step, right? So you get the blue part. You can then plug the blue part into this Q function here and look for the new pi and lambda that makes this whole thing as large as possible. So that's what we're going to do in the M step. We plug in the blue part with this thing instead, like N0 times this probability, right? And involve the pi odd lambda odds. We plug in this thing. We again take the partial derivative with respect to both pi and lambda. And we try to see when the two partials are equal to 0. Right? We solved for the pi and lambda values. Those are going to be our pi nu and lambda nus. If we solve for pi, or when the partial of q with respect to pi is equal to 0, you will notice that it simplifies to your pi nu is just going to be the NA0 divided by n, where essentially the NA0 is that expectation of NA given the old stuff and the observed data, essentially the blue part from the E step, and also this whole thing we saw over here. Like in each iteration, like pi old and lambda old are going to be some constants you already know, right, from the last iteration. You also know the observed N0. So this whole thing, the NA old is going to be a constant where you can plug in to here. You divide it by n, the total sample size. It's going to give you the pi nu, right, which is your new guess to what proportion of people come from the never drinker population A. If you solve for lambda in the partial of q with respect to lambda equals to 0, you notice that this whole thing is equal to 0 when your lambda is equal to this fraction over here, where our lambda nu is essentially the results where the numerator is given by the sum over the other classes with more than one drinks, the k times the n case, and the denominator is going to be the sum of the over the 6 classes from 1 to 6 of the n case, plus essentially the NB old, right, which is the 0 class, how many people are there observed, minus the NA old got from the E step. Something you notice over here is once you get the NA old, actually the pi nu and lambda nu looks just like the Bernoulli and the Poisson MLEs you have on the complete data. Right? You can notice that this pi nu over here essentially calculates the proportion of individuals out of all n individuals who are expected to come from group A, given our last guess of the parameters and the observed data. The lambda nu over here is essentially you're computing the average over the individuals from population B, right? These are either all of the individuals who report having more than one drink, one or more drinks, or that proportion of people who report having 0 drinks who are believed not to be an NA-old, the remaining individuals, N0 minus NA-old. You're essentially computing the average number of drinks that all of these individuals have. And that's how you computed the Poisson mean in the regular case. As long as you know that these many individuals are supposed to from class B. Okay, so let's try to implement this on the simulated alcohol data. Let's try and run the EM algorithm for a total of 15 iterations. Okay, so let's use the pi's and lambdas, which are 0 vectors right now, for storing the estimates. Let's say the initial guess to the pi, which is what proportion of people have 0 drinks, let's say is 50%. Now let's say out of the people who drink anything, the lambda initial value is equal to 1. And in each EM cycle, we're going to update these sequence. So this is our initial pi old and lambda old. The nth, which is the observed data, is essentially what we can get if we do table of the counts. And then the N0 is going to be the first entry of it, which counts how many people report having 0 drinks. We know that some of them come from the A class, some of them might be from the B class. Okay. So in each EM iteration, for t equals to 2 all the way up to 15, we're going to repeat the 2 E step and the M steps. In the E step, we essentially need to get the NA old, right? Conditioning on the old pi and lambda estimates that we have from the last iteration. What is the expected number of people we think out of the N0 class that truly never drink? So what we need to do is to compute that earlier thing we saw over here, right? You plug in the observed N0 and the current pi old and lambda old into this formula, to get your expectation of NA, which, well, we also call it NA old. Okay, so that thing we just saw earlier, we can compute the numerator and the denominator separately, take the ratio between them. That's essentially our NA old, right? It's going to be a number that tells you an expectation. How many people do we think come from the never drinker class, given the current parameter estimates? In the M step, we're going to use this NAT to figure out the new pi and lambda estimates. Essentially, we can see that the new pi estimate is just going to be this NAT or NA old divided by how many people there are in total in our sample, right? Which is essentially the sum of the nth vector counts over each possible class. The lambda's t, so the new lambda guess in this iteration is essentially going to be the average number of drinks taken by the individuals who are believed to come from the B class. So essentially what you can do is to say, we know the total number of drinks that these individuals are going to be having is, you can do like if this person, the number of people who have 1 drink times 1, number of people who have 2 drinks times 2, number of people, etc., number of people who have 6 drinks times 6, right? Which is essentially given by the sum of 1 through 6 of everything but the first entry of n's. Why everything but the first entry? Because the first entry corresponds to the people who have 0 drinks, right? Of course, you can also do the sum from 0 to 6 of the whole n's. It's going to give you the same thing. That's the total number of drinks taken by everyone. You want to divide that by the total number of people who you believe come from class B, right? What is that? It's the total number of people who have more than 0 drink plus N0 minus NA old, right? NA old is what we call NAT over here, which is currently what is our expectation of individuals who never drink. We want to exclude these people from taking the average for population B. That's going to be our lambda updated value. Okay, so suppose we iterate this for a total of 15 iterations. We will end up with 15 different pi and lambda estimates across the iterations. Right? You can see that we started with pi of 0.5 and lambda equals 1. In each iteration, these values got updated, and then it seemed to have stabilized, right, in the later iterations. Right? You can see that nothing seems to have changed in iterations 13, 14, and 15. How do you tell if the estimates are good, right? Let's recall how we generated the data. When we generated the data, we tried to generate the number of drinks someone has, where the true pi was given by, I think, 0.7. Right? So it's a little bit different from 0.75. And the true lambda for those 30% of people who ever drink was 3. And our estimate is about 2.755. So our estimates seem to be a little bit different from the true values we use for generating the data, 0.7 and 3, right? But it was actually more due to a finite sample deviating from the theoretical parameters we use to generate the data. If you have a larger sample size, expect these things to be better. How do I know? It's because if you actually take the group we just generated earlier, so the group membership of individuals, which was either 0 or 1, and you take the average of that, it essentially gives you, if we know the latent group membership, what proportion of people were actually generated to come from class A, right? And that was about 0.756, which you can see is very close to the pi estimate we get from the EM algorithm. If you take the individuals whose group is equal to 0, and you look at the mean of their counts of number of drinks. So this is essentially the lambda, right? Or if you know the group membership, how you would compute the MLE of lambda. That's about 2.78. And you can see that it's very close to our lambda estimate we got from the EM algorithm. What this means is that the results we got for pi and lambda from the observed data, not knowing the actual group membership, because we never use that in our algorithm. this is actually very close to the MLEs we get if we know the complete data, which we didn't have the luxury for. We didn't know the group membership. And this essentially means that our algorithm did very well. All right. So that was how we got the parameter estimates of pi and lambda using the EM algorithm for the ZIP model. If you're interested, for the remainder of the time, I want to talk a little bit about the sampling distribution of the marginal maximum likelihood estimator. And the MMLE here, which stands for the marginal maximum likelihood estimator, your guess is right. It essentially corresponds to, if we don't observe the latent variables or the missing data, what is the maximizer to the marginal maximum likelihood, or in other words, the observed data log likelihood or likelihood. So in our case, it's saying that if we don't observe the yi's, then what is the sampling distribution of the pi hat and lambda hat that we got in the earlier steps? Let us conduct a simulation study when we repeat what we did for a total of 1,000 times under the same two parameters of pi and lambda of 0.3 and 0.7 and 3. And in each replication, let's generate a new data set following the ZIP model of size 300. We store the MML estimates, which is essentially the results of the last iterations pi hat and lambda hat of each replication. So here's our setting. The true pi is 0.7, true lambda is 3. Our sample size in each replication n is 300, and our number of replications is 1,000. Here's a function that is essentially a wrapper to our earlier EM algorithm. The inputs include the data, which is the count data, and it's the number of iterations. Default is going to be 100. The initial value, and also the so these things. Right? By default, the initial values are 0.5 and 0.5. And in each iteration, what it's going to do is to first take the data, which might be, say, for 300 individuals, how many drinks there's reported they have. It first tabulates it into the 0 and 1 all the way up to n case. Nk in this case, for each data set can be different. It's the maximum number of people who report the maximum number of drinks. So it's not necessarily 6. It takes the initial values of pi and lambda, and then it repeats the EM algorithm we saw earlier for a total of, by default, 100 iterations. This function is going to take these inputs and return two things, which is the pi and lambda from the last iteration, which are essentially our pi hat and lambda hat that we have obtained using the EM algorithm. So right now we're ready to do the simulation. Just like before, in each replication, we first generate the data. We use the generated data to estimate the parameters, and we store the parameter estimates and compare them to the true values for generating data. Generating data is essentially how we generated the ZIP and zero-inflated Poisson data, right? When we generate the data, we first generate the group membership, and then conditioning on group membership, we generate the counts. It's either 0 or a Poisson. And then using this data, we plug it into the EM zip function we just created. We'll plug this data in, and it's going to store for us, for that replication, what were the pi hat and lambda hat, the output of the EM algorithm. The resulting EMS, which is the result of 1,000 replications of this, is going to be a 2 by 1,000 matrix. And you can imagine that the two rows correspond to the 1,000 replications pi hat and lambda hat. So let's give the row names, pi hat, lambda hat, and we can calculate the row means in this case, right? It's going to tell you across the 1,000 replications, what was the average estimated pi hat. It's really close to the true value of 0.7 this time, because we know that on average it's supposed to be close to the true value. Lambda cat as well is very close to the true value of 3, which we use to generate the data of each replication. Although in each single replication, the estimates could be different due to random fluctuations. If you're interested in the MSE of the two estimators, let's recall that what we can do is to take the average of the square deviation between our estimate of each replication and the true value we use for generating the data. For pi, what we can do is to take the first row of the EMS, which contains the 1000 pi hats, and take their average square deviations from the true value of pi, which is 0.7. And we can see that the resulting MSE is really small. For lambda, we can do essentially the same thing where we subtract the estimate from each iteration from 3, the true value, right? And we can see that the MSE for lambda was about 0.04. What we can also do is to look at the empirical distribution of the estimates across the 1000 replications. This can be done by just looking at the histogram of the first and second rows of EMS, which are essentially the pi hats, lambda hats across the 1000 iterations. The left plot gives the histogram of the pi hats. Right plot gives the histogram of the lambda hats. Something you notice, first, they're all centered around the true values. That's good. The other thing is that they approximately follow some sort of symmetric distribution that's bell-shaped, which you might guess that it's a normal distribution, right? So the MMLE turns out just like the MLE. As your sample size goes to infinity, it's asymptotically normally distributed. It's consistent, meaning that as your sample size goes to infinity, the estimates you get should be conversion in probability to the true value that you use for generating the data. And across the replications, or in general, it should be normally distributed, or the center is the true value. So more rigorously, if you use theta to denote the p-dimensional true parameter, so here are the true, pi, and lambda, two-dimensional true parameters, then indeed, the standard results on consistency and asymptotic normality of marginal MLEs suggest that as your sample size goes to infinity, if you multiply the deviation between your theta hat, which is the finite sample estimate, the estimate to these parameters from a sample of size n, and the true theta, and you multiply this thing by the square root of the information matrix, or the Fisher information matrix. I included a link over here which you're interested in. That's also something you can consistently estimate from the data. If you take the product of these two things, it actually converges in distribution to a multivariate standard normal distribution, where the mean is 0 and the covariance is given by the p-dimensional identity matrix. So that's essentially the multidimensional version of the central limit theorem. However, if we only have one observed data set, and especially if your data set is small, how do you estimate the standard error of your MMLE parameters? So maybe sometimes, in addition to getting like point estimates to lambda and pi, what you also want is some kind of standard error to them, right? You can apply the earlier asymptotic normality results. Essentially, what it tells you is that the asymptotic standard error as the sample size goes to infinity of this theta hat will be given by the square root of the diagonals of the inverse of the Fisher information matrix. You can look up the formula to this thing on Wikipedia if you like. But as you can see, that this is a large sample approximation, meaning that it's going to be not so accurate if your sample size is small. And which we don't talk about over here, evaluating and inverting the Fisher information matrix is usually quite demanding. But let's not forget that maybe half a semester earlier, we learned about the powerful tools of bootstrap and jackknife, which are non-parametric methods or resampling methods we can apply to obtain standard error estimates. So that's something we can do over here. You can try to do non-parametric bootstrap to estimate the standard error of pi hat and lambda hat. Essential idea is very similar to how we did Bootstrap a long time ago. Essentially, you're going to rerun the EM algorithm and re-estimate the pi hat and lambda hat using different kinds of resamples of the data. Each resample, which is sample of size 300 in this case, with replacement, is going to be one Bootstrap replication. So using a resample of the original data, what you can do is to re-estimate, given this resample, what are the pi hat and lambda hat using the resample of size, say, 300. You repeat this process for a total of large B times, so that can be 200 in this case, since we're only interested in standard error estimates. And you can store across the Bootstrap replications, 200 of those, what were the corresponding pi hat and lambda hat obtained from the resamples of the original data. Okay, I didn't explain too much of the code over here because I assume you guys should have learned Bootstrap pretty well. Essentially, in each replication, we first resample the original data and we run the EM-zip, which essentially plugs in the resampled data and gives us the pi hat lambda hat for that data set. The resulting EM-boot, which is the output of the replicate, has a total of 200 columns corresponding to the 200 Bootstrap replications. The two rows again are the pi hat and the lambda hat. Now we know that if we want the Bootstrap standard error estimate, we can simply obtain what is the standard deviation of these two rows across the 200 replications. In this case, they're given by, for pi hat is about 0.026. You can see it's actually quite close to, if we take the earlier 1000 replications, what is the standard deviation of the pi hats across there, right? For the lambda hat, our Bootstrap estimate to the standard error is about 0.16, which is a little bit different from what we got from the Monte Carlo 1000 replications, but you can see that the scale is actually quite similar. So that wraps up the EM algorithm, and you can see that it's actually a very powerful tool for you to run a bunch of latent variable models in statistics.